Okay, so this second time, doing the step 3, when we need to solve this differential equation, right, this initial value problem, one of the things I want to note is that we can't use the theorem 8.3.2. So originally that's what I was going to do, is I was going to use the theorem 8.3.2, because notice that that theorem gives us the Laplace transform for y double prime as s squared y of s minus y of 0 and then minus, or sy of 0 and then y prime of 0. I think that's what it is. It just crashed.
Did the other video?
Nope, it's still going. It's still going. The other video is still there. Okay. So, I think this is what it is. Let me write down you can verify. Yeah, minus y prime minus s, yeah. So this is it, right? So the reason why we can't use the theorem from section 8.3 is because in order to use it, we need to know y prime of 0 and y of 0, and we only have y of pi over 2 and y prime of pi over 2. Okay, so what do? We need to solve this IVP, and one way to solve the IVP, one option, is to use variation of parameters. Use variation of parameters. So this is what we learned back, and I think this was on exam 3. So this is on exam 3. Right, so we've got an IVP, second order, right? So step 1 is to solve the homogeneous differential equation. Step 2 is to create a system of create a system of equations and solve for u1 prime and u2 prime, right? So you may have your complementary, then you have your particular solution, and then you add them together, and then you plug in your initial constraints, and that will allow you to get your to turn your general solution into a solution to the IVP. So you can do that. Here's another option, which is a lot faster. The second option is to, and I'm crossing this out because that was for another problem that I was doing. I just printed this out. So I just used dsolve. And remember, dsolve is what allows us to, dsolve is a command that allows us to solve differential equations as well as initial value problems, right? So I used dsolve and I plugged in my differential equation. So let's see here. So I'm trying to see what's a good way to do this. So I plugged in my differential equation, which is right here, the y double prime, right, equals -1. Remember, we use the 2 equal signs to indicate that we're not creating a variable, but we're actually inputting an equation. Then I put in my first initial condition, which is that y of pi over 2 is equal to 0. And I put in my second initial condition, which is that y prime of pi over 2 is -1. And then comma, right? And so then I needed to indicate what's y of x and then what is x, okay? And then shift enter, and I got this solution here. So this gives me, this is the result of step 3. And now for step 4, I'm supposed to combine my result from step 1 with my result from step 3. And I have my, obtain my solution. So my solution is y equals y naught of t y1 of t. This is for t in between 0 and t1, and this is for t greater than or equal to t1, right? So now this right here is my y1. So that's y1. And what was my y naught? Yeah, y naught is here. So let me copy this. Copy. And paste. Okay. So let's put it all together here. And I get my solution as y equals 1 plus cosine t minus sine t, and negative 1 plus cosine t plus sine t. And the domain here is going to be from 0 less than or equal to t less than pi over 2. And for my second equation, I'll have t greater than or equal to pi over 2. Okie dokie. So this is my final answer for the solution to this IVP. Okay. All right. So that's one method for solving our IVP. Okay. Now I want to show another method, and I'm going to briefly highlight the second method. Okay. So the second, let me add a page below. So the second method would be the following. So we want to still solve our IVP, which is y double prime plus y equals f of t, right? With y of 0 equals 2 and y prime of 0 equals negative 1. And f of t equal to 1 if 0 is less than or equal to t is less than pi over 2. And negative 1 if t is greater than or equal to pi over 2. Now what we're going to do to solve this IVP, and I think this is a lot faster and a lot easier. So use whichever method you prefer, but this is definitely a good method to use. What we're going to do is basically, step one would be to rewrite our f in terms of the unit step function. So we could rewrite f of t is equal to 1 plus u of t minus pi over 2 times negative 1 minus 1, right? Because remember, it is f0 plus u of t minus tau times f1 minus f0. Okay, now what is this? This is 1 plus u of t minus pi over 2 times negative 2. So we can write this as 1 minus 2 u t minus pi over 2. Okay, now we can take the Laplace. So our differential equation that we're trying to solve, so if this is our original diffie, right, is star. So we can rewrite star. So this is star. We can rewrite star as y double prime plus y equals 1 minus 2 u t minus pi over 2. And y of 0 equals 2, y prime of 0 equals negative 1. Y of 0 equals 2, y prime of 0 equals negative 1. Okay. Now take the Laplace transform on both sides. Okay. On the left-hand side, I will have s squared y of s minus y prime of 0 minus s y of 0 plus y of s And on the right-hand side, I'll have the Laplace transform of 1 minus 2 times the Laplace transform of u of t minus pi over 2. Okay. Now, y of 2 is equal to 2. Sorry, y of 0 is equal to 2. Y prime of 0 is equal to 1. The Laplace transform of 1 is 1 over s. And now I just need the Laplace transform of u of t minus pi over 2. To get the Laplace transform, let's add a page below. So to get the Laplace transform of u of t minus pi over 2, we're going to use that formula that the Laplace transform of u of t minus tau times g of t is equal to e to the negative st times the Laplace transform of g of, let me erase that because that's just hard to read. The Laplace transform of u of t minus tau times g of t is equal to e to the negative st times the Laplace transform of g of t plus tau. So in this case, my g of t is just 1, and my tau is pi over 2. So this Laplace transform is equal to e to the negative pi over 2 times s times the Laplace transform of g of t plus pi over 2. But what is g of pi over 2? G of pi over 2, g of t plus pi over 2, that's just going to be equal to 1, right? Because if g of t is equal to 1, then g of t plus pi over 2, that's just equal to 1. So we've got e to the negative pi over 2s times the Laplace transform of 1. And we know the Laplace transform of 1 is 1 over s. So I have e to the negative pi over 2s over s, right? Because the Laplace transform of 1 is 1 over s. Let me see that. So we can write that as e to the negative pi over 2s times 1 over s. Right, so we have e to the negative pi over 2s over s. Okay, so now plug that in down here. That is e to the negative pi over 2s over s. And putting it all together, we'll have s squared y of s minus 1 minus 2s plus y of s is equal to 1 over s minus 2 e to the minus pi over 2s over s. Okay, add a page below. And now let's go ahead and copy, paste. Okay. So now we're going to try to get y of s by itself, big Y of s by itself. I'm going to combine this term and this term. So I should have 1 plus s squared times y of s minus 1 minus 2s is equal to 1 over s minus 2 e to the minus pi over 2s over s. Okay. Add 1 plus 2s to both sides. So plus 1 plus 2s plus 1 plus 2s. 1 plus s squared times y of s is equal to 1 plus 2s plus 1 over s minus 2 e to the negative pi over 2s over s. So then y of s is equal to 1 plus 2s plus 1 over s minus 2 e to the negative pi over 2s over s, all of that divided by 1 plus s squared. Okay, and now To get y, I'm just going to take the inverse Laplace, right? So to get my solution y, little y, I need the inverse Laplace of all this stuff. Copy, paste, resize. Okay, and to get that inverse Laplace, I'm going to use Mathematica. So much, let's see here. So I've got inverse Laplace transform. Okay, I need parentheses. I got to be careful with my parentheses. So I'll have 1. Okay, in fact, I'm going to put the denominator in first. 1 plus s squared. Okay, and then s and then t. Okay. Now for my numerator, I will have 1 plus 2s plus 1 over s, okay, minus 2 exp of, and I need negative pi times s over 2. Okay, so I've got the exp. Okay, and then all of that needs to be over s. Okay, this is, we'll see. I probably messed up some of my parentheses, but let's see. Okay. All right, so here's the printout. Here's what you get for the printout. The printout, when you do your inverse Laplace transform, is you get 1 plus cosine t plus 2 heaviside theta, okay, and then negative pi over 2 plus t, so negative pi over 2 plus t. I think I'm running out of room here. Times negative 1 plus sine t plus sine t. All right. And so now, what is this? This is, believe it or not, related to, this is related to the, so the heaviside theta, let me just check this out. I believe that this is the same as our step function. So let's go. Heaviside theta should be the same as our yes. So this heaviside theta is Mathematica's way of writing u. So this is the same as our unit step function. So this ends up being u of t minus pi over 2 times sine t minus 1. Okay? And then this is plus sine t plus cosine t plus 1. So we've got sine t plus cosine t plus 1 plus 2 times this. Okay? And this is yet another way of writing, this is another way of writing the solution to our, this differential equation that we had right here, right? So if we were to take this differential equation and rewrite this, not this differential equation, if we were to take this function and rewrite it using the unit step function, we would have 1 plus cosine t minus sine t, okay, plus u of t minus pi over 2, right, times this minus this, negative 1 plus cosine t plus sine t minus 1 plus cosine t minus sine t, right? And so then we get negative 2, and then the plus 2 sine, and that would cancel. So that would be the same as what we have here with our Heaviside function, or Heaviside step function. Okay. So there you have it. There we go. That is this way. So this second way of solving it is the way that I would actually recommend. So instead of doing the step 1, step 2, step 3, but you can do either way if you want, right? So you can do step 1, step 2, step 3, step 4, or you can do this method here where you convert. So let's just to review, what are we doing here? So you convert your piecewise continuous function into a function involving the unit step function, and then you take the Laplace transform of both sides, and then you solve for big Y of S, and then once you solve for big Y of S, you then take the inverse Laplace transform, and then you just got to remember that the Heaviside theta is Mathematica's notation for the unit step function. Okay.